In this video, we pick up where we left off in our last video on solving inclined plane problems. So let's go back up here and remind you that we have an inclined plane with a block on it. The block has an initial velocity of 0. It's going to slide down an inclined plane, and we're being asked to find its speed at the bottom of the plane. The height of the incline h is 5. I'm going to call this initial position 0. I've set my x-axis along the inclined plane as we talked about in the previous video, and when it gets down to this location, the bottom of the inclined plane, this distance is L. And this length, this L, is related to the hypotenuse of a triangle. So h divided by L is the sine of 30, and so I'm going to be able to use that fact. Now, we found, after having worked through the problem with the free body diagram, solving Newton's equations, we found the acceleration, and most importantly, we found that acceleration was a constant. And so we're now going to start using the kinematic equations. Like any problem with the kinematic equations, we need to set it up. So I've got my little column here. My initial position, as I said, was 0. My final position is going to be L. But by trig, we see that that's h over the sine of theta. Vx naught was 0 meters per second. I don't know what the final velocity is. I have the following set of equations for the kinematic equations. X equal x naught plus Vx naught t plus 1/2 axt squared, where this is 0 and this is 0. I know that the final speed is equal to the initial speed plus the acceleration in x times t, and I know that this is 0. And the final speed squared is equal to the initial speed squared plus 2 times acceleration times the change in x. And again, I can simplify that equation some. So these are the setup of the problems, and now I need to actually work this just like I would have worked any problem back in chapter 2 in one-dimensional motion. So when we're sitting here looking at this problem, I don't know time, I want to find Vx. This equation doesn't have Vx in it, so it's not my first choice for attacking the problem. This has Vx, which is unknown, I want to solve. Ax, yes, I know g, and in fact I know theta. Theta was 30 degrees, so I could find the acceleration. But I don't know t, so I'd have two unknowns. Now I could use this equation up here to find t, substitute in here, and find Vx, and that would be a perfectly acceptable solution. But we're going to look for something simpler. Here, I'm looking for Vx. I've got 2 and Ax, which I know, and Lx, which I know, so everything here I know except Vx, which is what I want to solve. So this is the simplest, most easiest direct approach to attacking the problem, is to solve this equation. So I'm going to do that. Vx squared is 2 times g sine theta. And then I want to put in x. X is L, but that's h over sine theta, the height divided by the sine theta. Notice the sine theta cancels out, and Vx squared is 2 times g times h, or Vx is the square root, and it's moving in the positive direction, gh. Notice that the angle of inclination doesn't enter into the thing. Again, this is one of those things that you learn to pick up by not plugging numbers. It turns out this equation says that whether the incline looked like this at some height, or whether the incline looked like this with the same height but not nearly as steep, by the time the block gets to the bottom, it would have the same speed, even though it would have followed a different path. This is because it was frictionless. In fact, had it even just been dropped, which is equivalent, remember, to an incline of 90 degrees, had it just been dropped a height of h, right before it hit the ground, it would have the same speed. This is a very unique fact about this type of force, gravity. And we'll come back and talk about that later when we talk about this idea of potential energy. All right? You don't get these sort of understandings by plugging numbers in. Theta doesn't even enter into the problem. All right, plugging in the numbers here, we have the square root of 2 times 9.8 meters per sec squared times 5 meters. So Vx is approximately 9.9 meters per second. And that's the speed of any time an object drops 5 meters of height, regardless of the way it follows. In fact, it's true even if it follows a path maybe like this path, where here's the block and here's the path. That can be seen as a series of inclines whose angle is changing. Now, once you get this answer, you go back and see if it makes sense. Well, another advantage of having done this in symbols and not numbers is that when I look at this speed, Vx equals square root 2gh, if g was to go to 0, then Vx would be 0. In other words, if there was no gravity, the object wouldn't have any speed. It wouldn't move. If you make h bigger, that is, if you drop it from higher up, it's going to move faster. So, g equals 0, Vx equals 0 meters per second. Makes sense? Larger h, larger speed Vx. And in fact, if you want the speed to be twice as much, you need to make the height 4 times as great, because it only goes as a square root. If you want the speed to be 3 times larger, you need to drop it from a height 9 times higher. Again, this is why we want to work in symbols, and we don't want to plug numbers in up here on the first set of lines, as you'll never be able to work harder problems in which they don't give you stuff. For instance, it is a waste of time to measure the angle of inclination. There would be error in that measurement, and it's a waste of time because the final result says that the only thing you really need to measure is this height. You don't need this length, you don't need this angle, you need this height, and you need to know gravity, and that's it. And you don't get that if you're plugging numbers in. Alright, so every type of problem you work in physics differs a little bit, but here's some things that are true about all of them. You always need a good drawing. You want to write down all the known quantities as well as what you're required to find. You want to write what you were given and what you need to find. Number 3 is the hardest one. You must identify the important physics that's involved. Often in the real world, you have friction. You have objects that aren't perfect. We model, that is, we assume things are perfect in order to get an approximate answer. Then, as an engineer or physicist, as we try to improve that for a real-world object, like a plane, for instance, then we'll use wind tunnels and other experimental data to try to get us a little refinement to the model. But we always have to start with some sort of perfected model, with some sort of physics idea in order to get at least close. It costs a lot of money to do experiments in the real world. In some cases, hundreds of thousands of dollars, maybe even millions. So you can't just willy-nilly do a bunch of experiments until you kind of luck out and hit the right answer. You have to have a model to start the problem. And that's what we're teaching you to do by doing these type of problems. It's like lifting weights to get ready for football, or playing scales so that you get good at playing an instrument so you can really play real music. Not so you can play the scales, and not so a football player can lift weights, but so he can play football on Friday night. Then you need, after you've identified these physics concepts, that will tell you which equations in physics might be helpful. And so you want to write those down. And it may turn out that you're wrong. It may not be useful for a particular equation. But writing them down will help enable you to see the equations, and it'll help you find the solutions. Once you've done that, then you need to do something else. You need to use definitions in the physics that you've done before and try to solve the problem. And it may be that you can't solve it directly. It may be that when I first looked at the problem, I didn't know a formula about speed Vx. But what I did know was how to find acceleration. So instead of just working the problem I was given, I solve for something I know I can find. Then once I find it, I go back and I start the process over again. And I keep finding things until I eventually can cut the trees down and I can find the way out of the forest. It's nice if in the forest you have a map and you can just find the road and get out. If you can't, you start cutting down trees. If you cut the whole forest down, you'll be able to find the road. Alright, that finishes this video on dealing with inclined planes.